What can we truly know? Philosophers have pondered this for centuries, but now scientists and mathematicians are joining the conversation, revealing surprising limits to human understanding. Consider a simple chessboard puzzle. Covering it with dominoes is easy, but remove two opposite corners, and the task becomes impossible. Not difficult, impossible. Each domino covers one black and one white square, but the mutilated board has uneven colors. No amount of effort or computing power can change this fact. This video explores such boundaries. Some problems computers cannot solve quickly or ever. Physical systems prove too complex to predict. Logical statements exist that are true but unprovable. Paradoxes serve as our guides. When valid reasoning leads to contradiction, we've discovered an assumption that doesn't belong. Self-reference appears throughout, in language, math, and computing, creating similar limitations across different fields. What does this mean for science, mathematics, and our quest for knowledge? Join us as we explore where reason reaches its limits. Language holds a mirror to itself, creating fascinating puzzles. The classic liar paradox is a sentence declaring its own falsehood. If true, it must be false, and if false, it becomes true. This self-reference appears in many forms, from two sentences that reference each other to Yablo's paradox, an infinite chain where each statement declares all later ones false, creating contradiction without any circular reference. Numbers face similar challenges. The Berry paradox describes the least number not expressible in fewer than 11 words. A 10-word phrase that supposedly describes a number, requiring at least 11 words to express. Richard's paradox constructs a number deliberately different from every English description of numbers between 0 and 1. Yet the construction itself becomes another description. These paradoxes reveal something essential. Language, for all its power to describe reality, contains inherent limitations. When words turn back on themselves, they expose the boundaries of what can be consistently said, reminding us that the map is never quite the territory. Have you ever thought about what makes you, well, you? Are you the same person you were 10 years ago? What about the ship of Theseus? If you replace every single plank of a wooden ship, one by one, is it still the same vessel? These questions might seem simple, but they touch on one of philosophy's most persistent puzzles, the problem of identity. Everything changes over time. Trees lose their leaves, mountains erode, and even our own bodies are in constant flux. Most of our cells are replaced every 7 years. So, if a person's body completely changes over time, in what sense are they still the same individual? Some philosophers argue that a person is their body. But if that were true, then after 7 years, would someone be the same person who committed a crime? Others claim that identity lies in the mind, our memories, thoughts, and consciousness. Yet personality changes, amnesia, and even the natural evolution of our beliefs challenge this view. And then there's the idea of a soul, an unchanging essence that defines who we are. But if the soul is unchanging, how does it connect to a constantly changing person? Here S where things get interesting. Perhaps these questions are impossible to answer because the objects themselves don't have fixed definitions. When children learn to recognize a spoon, their mother, or even the concept of family, they aren't learning exact definitions. They're learning to group sensations and stimuli together. Society teaches them to call certain things by certain names, and as long as everyone agrees, communication works. But the ship of Theseus doesn't have an objective existence outside of our minds. It's a collection of sensations we've agreed to label. The same goes for you and me. We are real as physical matter, but the idea of a continuous, unchanging self might be something we construct rather than discover. Identity remains deeply meaningful. The answers to these questions aren't found in the world, but in how we choose to see it. Infinite sets behave in ways that challenge our everyday intuition. While finite sets follow simple rules, a proper subset always has fewer elements. Infinite sets rewrite the rulebook entirely. Consider the natural numbers 0, 1, 2, 3, and so on. Now look at the even numbers 0, 2, 4, 6. Common sense says there should be twice as many naturals as evens. Yet, a perfect pairing exists. Match every natural number n with the even number 2n. This one-to-one correspondence proves these sets are the same size. The part equals the whole. This counterintuitive idea extends further. The set of integers, positive and negative, also pairs perfectly with the natural numbers. Even the set of all fractions, which seems infinitely denser, matches up with the naturals through a clever zigzag pattern. Mathematicians call sets that can be paired with the natural numbers countably infinite, with size Aleph null. But not all infinities are equal. Georg Cantor discovered this by examining the real numbers between 0 and 1. Try listing them in any order, and a new number can always be constructed by taking the diagonal digits and changing each one. This diagonal number differs from every number on the list. The interval 0 to 1 is uncountably infinite, strictly larger than the natural numbers. The power set of any set, the collection of all its subsets, is always larger than the original set. This creates a hierarchy of infinities. Aleph null, then 2 to the Aleph null, then 2 to that, stretching upward without end. These distinctions matter. Calculus, the language of modern physics and engineering, rests on these precise notions of infinity. Every bridge and rocket depends on mathematics that treats different infinities as real and distinct. Yet set theory itself contains puzzles. Russell's paradox asks, does the set of all sets that don't contain themselves contain itself? Either answer leads to contradiction. To avoid such problems, mathematicians developed axiomatic systems like Zermelo-Fraenkel set theory. Questions remain. Is there a set size between the naturals and the reals? The continuum hypothesis asks this, and we now know it can be neither proven nor disproven from standard axioms. The axiom of choice, which seems intuitive, leads to the Banach-Tarski paradox. A sphere can be cut into pieces and reassembled into two spheres identical to the original. These results force deep questions about mathematical truth. Do mathematical objects exist independently of human thought, waiting to be discovered? Or are they human inventions, useful fictions that follow consistent rules? Either way, the mathematics of infinity works remarkably well at describing our universe. Computers operate as logical machines, following precise instructions without emotion or guesswork. They excel at many tasks, from adding numbers to sorting information. Adding two 100-digit numbers requires about 10,000 operations, something modern computers handle in fractions of a second. Searching through alphabetized files using a binary search method takes only about 10 checks for 1,000 items, compared to 1,000 checks with basic searching. Some problems that sound simple actually demand extraordinary amounts of work. The traveling salesman problem asks for the shortest route, visiting multiple cities and returning home. For just 100 cities, checking every possible route would take billions upon billions of centuries, even with the fastest computers. The Hamiltonian cycle problem looks for a path, visiting every point in a network exactly once. The set partition problem asks whether numbers can be split into two groups with equal sums. The subset sum problem seeks a group of numbers adding to a specific total. The satisfiability problem determines if a logical statement can be made true. All these share a common difficulty. The only known reliable methods require checking every possibility, which grows exponentially with size. Faster processors, parallel computing, or even quantum computers cannot overcome this fundamental barrier. The time required remains astronomically large. These problems connect to each other. Solving one efficiently would solve them all. Researchers call them NP-complete, representing the hardest challenges in a class called NP. Whether efficient solutions exist is an open question worth $1 million from the Clay Institute. Most experts suspect no such solutions exist. Since exact answers often remain out of reach, approximation methods help. A traveler might always go to the nearest unvisited city next. While not guaranteed to find the shortest route, this approach works quickly and often produces reasonable results. Similarly, pairing largest and smallest numbers helps approximate solutions to partition problems. Some problems demand even more resources, requiring space rather than time. Generalized games like large-scale tic-tac-toe or chess fall into these categories. Understanding these limitations reveals the true nature of computation. Certain questions, though simply stated, resist simple answers. What tasks lie forever beyond the reach of computers? Problems that can never be solved, no matter how powerful the machine. Consider the halting problem. Given a program and its input, can we determine if it will eventually stop or run forever? This seems like a straightforward question with a clear yes or no answer. Yet, in 1936, Alan Turing proved it is impossible for any computer to solve this problem for all possible programs. The proof uses self-reference. Imagine a program that takes another program as input, asks whether that program would halt on itself, and then does the opposite, halting if it would loop, looping if it would halt. This creates a logical contradiction, showing that no program solving the halting problem can exist. This limitation extends far beyond one problem. Determining whether a program ever prints the number 42, whether two programs are equivalent, or whether a program always outputs 0, all are undecidable. In fact, Rice's theorem proves that any non-trivial property about programs cannot be decided by another program. The scale of this limitation is staggering. While there are infinitely many sets of whole numbers a computer can recognize, the sets it cannot recognize are uncountably infinite, vastly more numerous. Computers can only perform a minuscule fraction of possible tasks. Beyond the computable lies a hierarchy. Problems unsolvable by ordinary computers might be solved with hypothetical oracles. Yet each oracle creates new problems it cannot solve, forming an infinite ladder of unsolvability. This raises profound questions about minds and machines. Can human consciousness solve what computers cannot? Or are we, like computers, bound by these same limitations? The answers remain as elusive as the problems themselves. Science is humanity's most powerful tool for understanding the physical world. It gives us formulas to describe how objects move, how energy transfers, and how the universe functions. But perhaps the most fascinating part of science is not what it can explain, but what it cannot. This is the story of the boundaries of scientific knowledge. Let's start with a simple story. A man walks down a street. A roofer drops a tile. The man is gone. Had he left his house a few seconds later, he would have lived. Had the roofer's fingers been slightly drier, the tile wouldn't have fallen. This is a lesson about how tiny changes can create massive differences later on. We all understand this intuitively. If you had picked a different lottery number, if that pardon had arrived 2 minutes earlier, the world is complicated, and we know we can't predict everything. But what about small, simple systems? Surely, if we can perfectly describe how the parts interact, we can predict what happens next. For centuries, scientists thought so. Since Newton, the universe was seen as a perfect clock. Everything worked with total predictability. The mathematician Laplace imagined an intellect that knew the position of every atom and all the forces acting on them. For such an intellect, nothing would be uncertain. The future would be as visible as the past. But this optimism faded. In 1961, a meteorologist named Edward Lorenz was running computer simulations of weather patterns. He had a set of simple equations that produced realistic weather. One day, he wanted to repeat a simulation. Instead of starting from the beginning, he started from the middle. To save space, the computer printed numbers with only 3 decimal places. So instead of typing 0.506127, Lawrence entered 0 0.506. The difference was less than 1 part in 1,000. He expected the same weather pattern. He got something completely different. Lorentz realized that in these equations, tiny changes in starting conditions led to massive changes in outcomes. A slight change now radically altered the entire simulation later. This became known as the butterfly effect. The flap of a butterfly's wings in Brazil might set off a tornado in Texas. The butterfly's wing is the catalyst for a completely different weather pattern. Scientists call this sensitive dependence on initial conditions. Systems with this property are chaotic. A double pendulum is a perfect example. Two rods attached end to end swing in ways that are deterministic but unpredictable. You can write the equations, but to predict its motion long term, you would need to know the starting position with infinite precision. That's impossible. Chaos theory teaches us something crucial. Determinism and predictability are not the same. Determinism means the system follows fixed laws. Predictability is about whether humans can know the future. A system can be deterministic and still be impossible to predict. The Mandelbrot set, a famous mathematical shape, shows this complexity beautifully. It has a finite area, but its boundary twists and turns forever. The length of that boundary is infinite. To know whether a point lies inside the set, you need to know all of its infinite digits. Chaotic systems are the same. They demand infinite precision, and humans cannot work with infinity. Then there is the three-body problem. Newton gave us a simple formula for two bodies. But for three bodies, like the sun, earth, and moon, no simple formula exists. The moon's path around Earth is a three-body problem. This is why we can only give an average length for a lunar month. It can be up to 15 hours longer or shorter than that average. The problem is essentially unsolvable. The complex relationship between you, a pen, and the Earth is beyond the limits of simple scientific formulas. But chaos and complexity are not the end of the story. They are just the beginning. Quantum mechanics takes us much further into strangeness. Let's start with the double-slit experiment. Shine light through one slit, and it makes a simple pattern on a screen. Open a second slit, and you get an interference pattern. This happens because light acts like a wave. The waves from each slit interfere with each other. Now, here is the mind-blowing part. Physicists can fire photons one at a time. Even then, over time, an interference pattern appears. Each photon interferes with itself. How can one photon go through two slits simultaneously? It can't, but it does. This phenomenon is called superposition. An object exists in more than one place at once. We don't see superposition in our everyday world. When we look, an object is in one place. In quantum mechanics, when we measure a system, the superposition collapses to a single position. The question of why this collapse happens is one of the great mysteries of science. Before measurement, an object does not have a single position. It has many. The same is true for other properties like energy and momentum. Sewer position is the norm until we observe the system. And when a sewer position collapses, which position does it choose? The answer is random. There is no deterministic law. There are only probabilities. An electron has an 11% chance of collapsing to this shell, a 47% chance of collapsing to that one. But what it actually does cannot be determined. This is not an approximation. Quantum mechanics is the most exact science we have, but it tells us that, at the most fundamental level, the universe is not deterministic. Heisenberg's uncertainty principle adds another layer. There are pairs of properties, like position and momentum, that cannot both be known simultaneously. The more precisely you know one, the less you know the other. This is not a technological limitation. It is an inherent limit on our knowledge. The very act of measurement affects the system. The experimenter is intrinsically connected to the experiment. The properties of an object are only defined at the moment they are measured. This destroys a philosophical position called naive realism. This is the belief that objects have well-defined properties that exist independently of observation. In the quantum world, that is false. Properties depend on how and when they are measured. The Kachen-Specker theorem proves this mathematically. It shows that for certain particles, it is impossible to assign fixed spin values to all directions before measurement. There simply isn't enough room. The measurement does not reveal a pre-existing property. Rather, it creates the property. Schrödinger's cat makes this tangible. A cat in a box with a radioactive source is, until observed, in a sewer position of alive and dead. The weirdness of the subatomic world is transferred to the everyday world. Eugene Wigner took this further. He imagined a friend opening the box. Does the friend enter a sewer position? No. Wigner argued that consciousness causes the collapse. This suggests that consciousness is an active part of physics, rather than a mere byproduct. Entanglement shows that the universe is deeply interconnected. When two particles are entangled, measuring one instantly affects the other, no matter how far apart they are. Einstein called this spooky action at a distance. He thought it proved quantum mechanics was incomplete, but experiments have shown that entanglement is real. The universe is non-local. Measurements here affect objects across the universe. Reductionism, the idea that the whole is just the sum of its parts, fails. The whole is more than the sum of its parts. The entire universe is one system. Quantum eraser experiments push this further. By tagging which slit a photon goes through, you destroy the interference pattern. But if you later erase that information, the interference pattern returns. This means the photon's behavior depends on what will happen to it later. The outcome depends on the whole experiment, including future actions. This raises profound questions about time, causality, and free will. If human beings have free will, then particles might as well. If particles follow fixed laws, then humans made of particles also follow fixed laws. Science forces us to confront this. Relativity theory adds another dimension to this strange picture. Einstein showed that measurements of space and time are not absolute. They depend on the observer's motion. The speed of light is constant for all observers. To maintain this, moving objects experience length contraction and time dilation. Clocks on a fast-moving spaceship tick slower. The spaceship itself gets shorter. Far from being illusions, these are facts about the universe. Simultaneity becomes problematic. Two events that appear simultaneous to one observer may not be simultaneous to another moving at a different speed. Causality itself becomes murky. If you cannot agree on what happened first, how can you determine what caused what? Einstein also showed that mass and energy are equivalent. The famous equation E equals mc squared describes how they convert into each other. A moving object has more mass than a stationary one. A hot object weighs more than a cold one. Rather than being a fixed substance, matter is actually a form of energy. General relativity reveals that gravity is not a force in the usual sense. It is the curvature of space-time. Mass curves the fabric of the universe, and that curvature guides the motion of other masses. Space and time are dynamic and active participants in the universe, not merely a static stage for events. Quantum mechanics and relativity are both extraordinarily successful, but they contradict each other. They deal with different domains, but in places like black holes, they give conflicting predictions. A new theory is needed. Quantum gravity, string theory, loop quantum gravity, these are attempts to unify them. They promise even stranger conceptions of space, time, and reality. What have we learned? The true purpose of science is to build a deep understanding of the world, a goal for which prediction serves as an essential instrument. Chaotic systems show us that deterministic laws do not guarantee predictability. Quantum mechanics shows us that reality is not what we thought. Properties do not exist until measured. The universe is non-local and interconnected. Relativity shows us that space and time are relative. There are no absolute measurements. Our minds evolved to navigate a world of medium-sized objects moving at medium speeds. We should not expect them to easily grasp the quantum world or the relativistic cosmos. The universe works the way it works. It will not adjust to us. We must adjust to it. Science reveals the limits of reason, but in doing so, it reveals a universe far more interesting than we ever imagined. A universe where a cat can be both alive and dead, where two particles can be connected across the universe, where time slows down for a traveler, and where the very fabric of reality depends on how we look at it. To reveal such a universe is science's greatest triumph. Imagine checking into a random hotel room late at night. You walk in, and the closet is full of clothes. The shoes fit perfectly. The robe is your exact size and favorite color. Everything feels like it was made just for you. How could this be? That strange scenario mirrors a real question in science. Why does the universe feel perfectly suited for us? The laws of physics seem fine-tuned for life and intelligence. If gravity were slightly stronger, stars would collapse too quickly. If it were weaker, they would never form. If Earth were a little closer to the sun, oceans would boil. A little farther, and everything would freeze. The cosmological constant, a force that counteracts gravity, is calculated to the 120th decimal place. If it were off by a hair, the universe as we know it would not exist. These are not isolated examples. They point to deeper mystery. Scientists call this the Goldilocks enigma. The universe is not too hot, not too cold. It is just right for us. But why? To understand this, we have to separate three questions nested inside each other like Russian dolls. First, why is there any structure at all? Why does the universe have consistent laws that repeat everywhere and every time? Second, given that structure, why does it allow life to exist? Why are the laws capable of producing carbon, complex molecules, and enough time for evolution to unfold? Third, why did this life-sustaining universe produce creatures intelligent enough to understand it? Why do we have minds that can ask these questions in the first place? These questions are not new. Philosophers and physicists have proposed many answers. One ancient answer is that a creator set everything up this way. The universe was designed with life in mind. For those who accept this, the mystery is solved. But for those looking for a scientific explanation, this answer raises its own questions. Another possibility is that it is all a fluke. The universe just happened to turn out this way. There is no reason behind it. If it were different, we would not be here to notice. This idea is simple, but it does not really explain anything. It just accepts the mystery. Some argue that the universe is not actually fine-tuned for life. Look around. Most of the cosmos is empty and deadly. 2/3 of Earth is water. Large parts of land are uninhabitable. Hurricanes, earthquakes, and diseases constantly threaten us. If the universe were designed for us, it did a poor job. This response challenges the premise, but it does not answer why life emerged anyway. Others say our definition of life is too narrow. Maybe life could exist under very different conditions. Silicon-based creatures, neutron star beings, or even computer viruses might count as life. If we broaden our definition, many possible universes could support some form of life. This idea expands our imagination, but it still does not explain why our particular universe has the specific laws it does. One of the most popular modern explanations is the multiverse. Our universe might be just one of countless others. Each has its own laws and constants. Most are empty and lifeless, but in a tiny fraction, conditions are right for life. We happen to live in one of those lucky ones. It is like winning a cosmic lottery. There is no miracle, just statistics. There are many versions of the multiverse. In quantum mechanics, Hugh Everett suggested that every measurement splits the universe into multiple copies. In string theory, different universes exist on separate membranes, colliding and branching off. Some theories even propose that universes evolve through a kind of natural selection, with those producing more black holes having more offspring. And then there is the idea that every possible mathematical structure exists as its own universe. But the multiverse has critics. There is no evidence for any other universe. They are, by definition, beyond observation. Some say invoking a multiverse is no more scientific than invoking a creator. It is an untestable idea, and even if it works, it pushes the question back one level. Why do the laws of the multiverse allow for life-permitting universes? Another approach comes from symmetry. Scientists like Einstein and Emmy Noether showed that many laws of physics arise from symmetries. Conservation of energy comes from the fact that the laws do not change over time. Conservation of momentum comes from the fact that they do not change from place to place. From this perspective, the laws are not fixed things out there. They are just the patterns that remain when you look at the universe from different viewpoints. Arthur Eddington compared this to a fisherman using a net with 2-inch holes. He concludes that no fish are smaller than 2 inches. But that is not a fact about the ocean. It is a fact about his net. In the same way, the laws we see might reflect our methods of observation more than the universe itself. This idea is profound. It suggests that the structure we marvel at is partly our own creation. We impose mathematics, logic, and symmetry on the world. The universe does what it does. We are the ones who describe it with equations. As Eddington said, we find a strange footprint on the shore of the unknown. After much theorizing, we realize the footprint is our own. Yet this view also has limits. It seems to deny that there is any real structure independent of us. But the universe existed for billions of years before humans arrived. Were there no laws then? Did gravity stop working before anyone was around to observe it? Most physicists would say no. The laws are real. They do not depend on us. So where does that leave us? The truth is, we do not know. Not yet. Science has given us incredible answers, but some questions remain open. Maybe future discoveries will solve the puzzle. Maybe there is an infinite chain of explanations, each deeper than the last. Or maybe some things are simply beyond our reach. There is humility in admitting we do not have the final answer. The universe that gave us reason is also the universe that hides its deepest secrets. And perhaps that is the most honest conclusion we can reach. We are here asking questions in a universe that seems strangely right for us. Why? We can speculate. We can theorize. But for now, the mystery remains. Mathematics reveals its limits through several profound discoveries, starting with the ancient Greeks, who believed all numbers were rational, until Hippasus proved that the square root of 2 could not be expressed as a simple ratio. This irrational number was so troubling to the Pythagorean Brotherhood that legend claims they silenced him permanently. The Greeks also pursued geometric constructions, using only straight edge and compass. 3 classic problems, squaring the circle, trisecting an angle, and doubling the cube, resisted solution for 2,000 years. Only in modern times did mathematicians prove these constructions impossible. showing that pi is transcendental, and the cube root of 2 cannot be constructed with these limited tools. The tragic story of Évariste Galois illustrates another boundary. Before dying in a duel at 20, he developed group theory to determine when polynomial equations could be solved. While quadratic, cubic, and quartic equations have solution formulas, quintic equations generally do not. Galois showed that the symmetries of an equation determine whether ordinary operations can solve it. Computers face their own mathematical obstacles. The tiling problem, determining whether shapes can cover a floor without gaps, is undecidable. No computer program can always answer this question correctly. Similarly, Hilbert's 10th problem asked whether an algorithm could determine if polynomial equations have integer solutions. In 1970, mathematicians proved such an algorithm cannot exist. Perhaps most striking are Gödel's incompleteness theorems. Any logical system powerful enough to describe basic arithmetic contains statements that are true, but cannot be proved within that system. The famous Gödel sentence declares its own unprovability. If provable, it would be false. If false, it would be provable. This creates a permanent gap between truth and proof. These limitations reveal that mathematics, despite being humanity's most successful rational enterprise, has inherent boundaries. Yet each restriction points beyond itself. What cannot be done with straightedge and compass becomes simple with measurement. What remains unprovable in one system finds proof in another. The boundaries of reason are not walls, but horizons. We have journeyed through the limits of what we can know and prove. From the physical world, we see reason dictates that certain processes, like a time traveler creating a paradox, simply cannot happen. The universe forbids contradictions. Then we encounter limitations of the mind itself. Language and logic have boundaries. A sentence that declares its own falsehood cannot be given a stable meaning. To keep our thinking clear, we must avoid such mental traps. Practical limits also appear. Some problems, though solvable in theory, would take trillions of years to compute. Others, like the weather, are so sensitive that perfect prediction is impossible. And our intuition is often an unreliable guide, needing constant adjustment by science. So, what is reason? It is the set of processes that protect us from contradictions and falsehoods. When a line of thinking leads to an error, we know we have stepped over the boundary. And what lies beyond that boundary? Perhaps knowledge exists that we cannot access, but we already live beyond pure logic. Our lives are filled with love, art, and wonder. Things reason cannot explain, but that give life its meaning. Reason is a powerful tool, but it serves our will, our desires, and our humanity.